Hey guys, we've got our last lecture in this particular portion of chapter 16, and we want to talk about a chemical reaction. How does it get to equilibrium? All right, so I've written down the equilibrium constant equation here as a reminder again. And so this is the point that we want to make. Make sure that you understand these rules here. If we know what the correct K is, so if we know the value of K for a particular reaction at a given temperature, at equilibrium, right? That's what K is. That's this value at equilibrium. Then if we know the correct K and we calculate K, or what we think might be K, at a particular point in time in the reaction, in other words, if we take the concentration of the products and divide it by the concentration of the reactants and get a value, right? If that value is equal to K, then we know we're at equilibrium, right? If that value is less than K, then we know that we need the reaction to shift towards the products. How do we know that? Well, if this value is smaller than it needs to be, then we need this number on top of the fraction to get bigger, right? Which is the products, the concentration of the products. So we need more products and less reactants. So that means the top needs to get bigger, and we're going to go in the forward direction, right? If the value that we calculate is greater than the value that we know K actually is, then we need it to shift towards the reactants. In other words, the value is too large, and we need it to get smaller, and so we need the bottom of this fraction to get bigger and the top to get smaller. And so we need it to shift towards the reactants. It's going to go in this direction. All right, so let's do a couple of problems, and I'm just going to write this down real quick. If it's equal to K at equilibrium, all right, if it's less than K, we need it to go this way, and if it's greater than K, we need to shift towards the reactants. All right, so we'll just write that down as a reminder as we do these couple of problems here. And the problem's on page 493, example 16.4. And the problem says, a chemist is studying the following chemical reaction at 1100 K. All right, remember these K is only good at a particular temperature. So at 1100 Kelvin, we have this reaction here. 2H2S is going to produce 2H2 plus S2, right? All of these are gases, so they'll all figure into the equilibrium constant. And it says at that temperature, K is equal to 4 times 10 to the negative 6 molarity. So we've written that down right here so that we know what the correct value of K is. If the concentration of H2S equals 0.01 molarity, and the concentration of H2 equals 0.0022 molarity, and then the concentration of S2 equals 0.00011 molarity, is the reaction at equilibrium? And if not, which way will the reaction shift? Okay, so let's figure out let's calculate what would seem to be K at this particular. And I'm saying seem to be K, you understand, because we're going to calculate this, and if it doesn't equal this value here, then it's not really K, because K is this value at equilibrium, right? And we don't know if this is at equilibrium or not. So let's just write each of these things down. We're going to take the equation would basically be the concentration of H2, right, raised to the second power times the concentration of S2 raised to the first power, all of that divided by the concentration of H2S raised to the second power, right, that coefficient there. And so when we plug these values in here, we have 0.01 molarity. We need to write down our units so that we make sure we get the correct unit at the end, times I'm sorry, I did that wrong. That is not 0.01 there, and my eraser has flown away. I put the reactant in there. All right, 0.00022 molarity squared times 0.00011 molarity. All of that divided by 0.01 molarity squared. All right, and so we punch that in our calculator, and it says that we get a value of 5.3 times 10 to the negative 8. On the top here, we're going to have molarity cubed. On the bottom, we're going to have molarity squared. And so our final unit is going to be just molarity. So 5.3 times 10 to the negative 8 molarity. Now this number here is smaller than this number here. right, than the correct value of K. So if it's smaller, if the value we calculated is less than K, then what we need this reaction to do is shift towards the products. And so that's what it asks us. Is it at equilibrium? Nope. Needs to shift towards products. Right? So that would be the correct answer for this particular problem. Let's do one more. So our next problem says a chemist is studying the following chemical reaction. So they give us that NO3 minus plus 2H plus Ag yields NO2 plus H2O plus Ag plus. All right? And then they tell us that at room temperature, K is equal to 1.0. It's got the unit 1 over molarity. That's the value, the correct value of K. So the chemist measures the concentration of these substances and finds out that the concentration of NO3 is 0.8 molarity. The concentration of 2H plus the concentration of H plus is 0.12 molarity at a particular time. They tell us that at that point we have 15 grams of silver. NO2 has a molarity of 0.45. We have 150 grams of water, and the molarity of this Ag plus ion here is 0.36 molarity. Now, why did they give us the molarity for this guy, right, and for this guy? Because this guy's a solid and this guy's a liquid, and we don't include solids and liquids whenever we're calculating the equilibrium constant, right? So we don't have to worry about those for our particular equation. So let's go ahead and calculate what we think K is if we were at equilibrium. And so that would be this value here, 0.45 molarity, raised to the first power, because there's only a coefficient of 1 in front there, times 0.36 molarity. All of that divided by 0.8 molarity. I don't know why I'm writing concentration around that, because that would be if I wanted to, if I was just writing down the symbols first. So 0.45 times 0.36, on the bottom 0.8 molarity times 0.12 molarity, and this is the only one that doesn't have a coefficient of 1, it has a coefficient of 2, and so we raise that to the second power, right? So we punch that in our calculator and we get a value of 14. And when we look at the units here on top, we're going to have m squared. On the bottom here, we're going to have m cubed. So we're going to have units of 1 over molarity, which matches the units here, right? So if the correct K is 1, but we're at a value of 14 right now, then this number is larger than the correct K. And so when it's larger than the correct K, then we need it to shift towards the reactant. So is it at equilibrium? No. Needs to shift toward reactants. Right? All right. So that's the answer to that question. And that's the end of this section. So you guys let me know if you have any questions, and I will see you next time.